Hello everyone, I'm Hai-Long Kin. It's my pleasure to present our work, NeHaD, Neural Hamiltonian Deformation Field for Dynamic Scene Rendering. Thank you for being here, and let's get started. Representing and rendering dynamic scenes is pivotal for immersive imaging applications. Given discrete temporal video sequences, dynamic scene rendering aims to model scene dynamics and synthesize high-fidelity novel views at arbitrary timestamps in real time. It confronts two primary challenges. First, achieving high-fidelity reconstruction of complex dynamic scenes with rapid motions and topological changes. Second, maintaining real-time rendering efficiency with low training cost. This causes the fidelity-efficiency trade-off. Recent advancements in dynamic scene rendering have been achieved mainly through methods based on neural radiance field and Gaussian splatting. However, they either suffer from slow rendering speed due to the requirements for dense sampling along rays during rendering, or struggle to model temporally complex dynamics and properly differentiate spatial and temporal deformations. Therefore, they fail to achieve a good balance between fidelity and efficiency. So we have to ask, what actually makes dynamic scene rendering feel high fidelity? We argue that realistic rendering requires not only perceptual quality, but also physically plausible dynamics, which most current approaches have overlooked. Interestingly, we find that the processes of human cognition and scene rendering both follow fundamental physical laws, particularly Hamiltonian mechanics, demonstrating the natural applicability of Hamiltonian principles to dynamic scene rendering. Hence, our core insight is that Gaussian covariance matrices inherently exist on symplectic manifolds, making Hamiltonian mechanics a proper choice for mathematically reformulating Gaussian deformation fields. Here's the overall pipeline of NeHaD. Like other Gaussian-based methods, our approach follows the standard workflow: initialization, representation, deformation, and rasterization. Our key contribution lies in how we model the deformation field. NeHaD introduces three core innovations. First, a Hamiltonian neural network decoder that learns physically plausible deformations. Second, Boltzmann equilibrium decomposition for adaptive static dynamic separation. And third, physics-informed constraints to ensure robust dynamics. Now, let's dive into the details. Existing dynamic Gaussian splatting methods rely on purely data-driven MLP decoders to predict deformation fields, which often leads to physically implausible motions, such as abrupt appearance or disappearance of primitives. To address this fundamental issue, we propose to replace the standard MLP-based deformation decoder with an HNN that inherently respects the underlying physical laws governing dynamic systems. The Hamiltonian formulation ensures energy conservation, and canonical equations then generate symplectic gradients, which HNN learns to optimize. Unlike traditional MLPs that compute gradients only during backpropagation, HNN requires forward-mode gradient computation to construct vector fields from scalar potentials. This creates two challenges for high-dimensional Gaussian deformation. First, explicit position momentum coupling as input becomes intractable. Second, directly learning vector fields risks mode collapse due to the curse of dimensionality and lacks energy conservation constraints since energy is fundamentally a scalar quantity. We address these challenges through Hamiltonian neural network decoder. We first extract spatial temporal features from hex planes and map them to latent representations via an MLP. These latent representations serve as the actual HNN input. They implicitly encode each Gaussian spatial temporal state, capturing the geometric and kinetic information needed for phase space construction. Essentially, they act as generalized coordinates for our dynamical system. Instead of directly learning vector fields, we learn two scalar functions, f1 and f2. Through automatic differentiation, these scalar functions generate the conservative field Vc and solenoidal field Vs, automatically guaranteeing energy conservation and volume preservation. We also use lightweight attribute-specific adapters implemented as linear layers to process HNN-generated vector fields, maintaining standard dimensionality of each Gaussian attribute. While HNN ensures physically consistent deformation fields, a critical challenge remains: determining which Gaussian primitives require dynamic modeling versus those that remain static throughout the temporal sequence. Indiscriminate application of deformation to all primitives leads to computational inefficiency and potential artifacts in stable regions. To address this challenge, we introduce Boltzmann equilibrium decomposition. The insight of this mechanism is that only Gaussian primitives away from their equilibrium states should be activated for deformation. We formalize this through statistical mechanics, constructing soft masks based on Boltzmann energy distributions that adaptively filter out primitives useless to deformation. Position deformation requires careful spatial temporal filtering because not all Gaussians need to deform at every moment, and not all spatial locations are equally important at each timestamp. The decomposition pattern exhibits dual selectivity. We model this dual selectivity by constructing a phase space of the harmonic oscillator model, where each Gaussian primitive's equilibrium state is determined by both its spatial position and temporal context. The spatial and temporal equilibrium states are both initialized as Gaussian attributes and optimized during training. Scaling dynamics exhibit fundamentally different visual characteristics compared to position dynamics. The visual granularity of scaling changes is much smaller than positional changes, primarily affecting surface smoothness and appearance detail rather than global scene structure. Consequently, our decomposition strategy for scaling follows a different principle. We apply temporal-only decomposition for scaling dynamics, eliminating spatial constraints while maintaining equilibrium-based separation. Finally, this mechanism integrates into the deformation pipeline through equilibrium-aware blending, applying different decomposition strategies based on attribute characteristics. While HNN decoder and decomposition mechanism provide physically consistent deformation predictions and energy-based primitive selection, the temporal evolution of Gaussian attributes require additional physics-informed constraints to ensure stable and directed dynamics. We introduce two specialized constraints guiding the deformation process: second-order symplectic integration for position dynamics and local rigidity regulation for rotation dynamics. Standard Euler integration and higher-order Runge-Kutta methods suffer from energy drift and numerical instability, particularly for systems governed by Hamiltonian mechanics, due to violating simplexity. To ensure the long-term stability of our physics-based simulation, we use a symplectic integrator to update the position of each Gaussian. We have adopted the position-Verlet integration scheme, which requires both the current velocity and acceleration of a primitive. Accordingly, our HNN decoder is structured to provide both of these physical quantities. Rotation dynamics and Gaussian splatting present unique challenges due to the quaternion parametrization and the need to maintain local geometric coherence. Hence, we implement the local rigidity regulation, motivated by as rigid as possible, also known as ARAP. To ensure temporally smooth and geometrically stable rotations, we regulate the rotation updates to prevent unnaturally large changes between time steps. This is achieved by clamping the magnitude of the rotation angle. To prevent abrupt rotational changes, we further apply a smooth limiting function that constrains large rotations while preserving small natural rotations to get a clamped angle, thus constraining the rotation dynamics. Note that physics-informed constraints should be applied right after HNN decoder but before Boltzmann equilibrium decomposition. To evaluate the practical utility of NeHaD in graphics applications, we extend it to adaptive streaming for VR requirements, which is challenging in bandwidth-constrained environments. We adapt NeHaD to streaming through two enhancements. One is scale-aware anisotropic MIT mapping for efficient multi-level texture sampling, and the other is layered progressive optimization for global level of detail rendering. For scale-aware anisotropic MIT mapping, different scales from varying viewing distances are analyzed using anisotropic weights, followed by MIP-map level selection and trilinear MIP mapping for texture sampling. For layered progressive level of detail optimization, training proceeds progressively across different LOD levels, from lower to higher resolution, with Gaussian residuals obtained adaptively based on opacity to enhance the ground Gaussian at level 0 in a layered manner, to increase detail at higher rendering rates. Finally, we compare NeHaD with state-of-the-art models on 3 public datasets, and our method consistently outperforms baseline models in visual perception, delivering realistic renderings with coherent dynamic motion. Quantitative results are summarized in Table 1. NeHaD outperforms state-of-the-art methods across all quality evaluation metrics. Both quantitative and qualitative ablation studies demonstrate the effectiveness of our proposed modules. Qualitative streaming results imply the potential of NeHaD for bandwidth-constrained multimedia applications. Moreover, qualitative results demonstrate NeHaD's improvements in depth consistency, temporal coherence, dynamic stability, and rendering accuracy. In conclusion, this work introduces NeHaD, a neural deformation field for dynamic Gaussian splatting guided by Hamiltonian mechanics. Our method decomposes 4D spatial temporal representations using Boltzmann equilibrium decomposition and employs an HNN-based decoder to predict Gaussian deformations with physics-informed constraints that ensure robustness against scene perturbations. The approach extends naturally to bandwidth-constrained streaming applications with minimal modifications. Extensive experiments demonstrate that our method achieves improved rendering reality. While improvements achieved, our method also has limitations. For example, learning Hamiltonian introduces extra computational overhead, leading to reduced real-time rendering performance. Future work could explore more flexible neural operators and efficient rendering pipelines to couple with complex non-conservative forces, such as fluid dynamics. That's all for today's presentation. Thanks for your listening.